Tom Goreau, come on up. And we have your slideshow set up again. Would you rather use this mic or that one?
Doesn't matter.
You can walk around with this?
Yeah,
or?
I prefer to walk around. How's that? Now, where's the control, though?
The pointer?
Yeah, the control for the slides?
The pointer? Is that it? Yeah, it looks like it.
Okay, so this is advanced? Okay.
Tom Goreau, everybody.
Okay. Hey. Thank you. I was asked to talk a bit about Floresta de Tijuca in Rio de Janeiro, Brazil. I'm going to talk about, I talked about that last year very briefly, so I'm really going to race through it quite quickly here because I want to talk a little more about evapotranspiration, water cycles, and the potential for modifying temperatures. So that's really where I want to go. Okay, this is Floresta de Tijuca in Rio de Janeiro, and everyone who visits Rio de Janeiro, they look from the beach and they look up and there's this wonderful forest up above the city. And the Brazilians tell everyone that that's natural force and they protect it and shows what great stewards of nature they are. Okay, it's a false narrative. When Charles Darwin visited Rio de Janeiro in the early 1830s, these hills were completely bare. And what had happened is that all these bare mountains that Rio de Janeiro is famous for were covered with forest to the very top when the Portuguese showed up in 1504. And when the coffee boom hit in the late 1600s or early 1700s or so, they cut all that forest down. They planted coffee up and down the slopes. Every place they could reach, they cut down. People made a killing off the coffee. The soil all washed away, and then that's left these bare mountains behind that have never recovered. Okay, now, so you'll see the bare mountains up above and then below it the forest. But all that forest was cut down for coffee. And the result of that is that Rio de Janeiro ran out of drinking water. So in the dry season, there was no water. People would have to abandon the city. They'd have to go to the countryside. They'd have to find rivers. They were desperate. They simply had no water. And there was no doubt in anyone's mind that that was a human-caused problem. They knew that those rivers that used to run year-round dried up when they cut the forest down all around the springs. And there was no confusion in anyone's mind that if they wanted their water back, they had to plant the forest back. So what happened then is that the city of Rio de Janeiro hired a bunch of slaves. And a handful of men spent their careers, decades, climbing into the few remaining mountain tops that hadn't been cut down because they were just too inaccessible to reach. They were too steep. You just couldn't get up there to cut them down. And so these men went and they transplanted seedlings out of what remained, those little remnants of the forest that remained, and they planted this entire forest over about a 20 or 30-year period. And when the forest came back, the springs came back and the water supply came back, and that's still a major source of drinking water for the city of Rio de Janeiro. Okay, now, of course, there's about 12 or 15 million people in Rio de Janeiro, so it's not enough for everybody, so they have to, harvest it elsewhere, but this remains a major source of drinking water for the city. Now, I first visited Floresta de Tijuca more than 30 years ago, and it's Foster Brown who took me there. Where's Foster? Yeah, Foster is the one who told me the story, okay? I mean, what I know from Foster, okay? Really. And it's just a wonderful, beautiful forest. Now, a little later, one of our Brazilian graduate students, William de Mello, and I were working in the Amazon, and I'll come back to that a little later, measuring greenhouse gas emissions out of the forest. And we went and made measurements here in the Floresta de Tijuca, and we also climbed up into the few remnants of native forests that we could find in southeast Brazil, which aren't very many, and it was very difficult to get to them. And we made measurements of greenhouse gas emissions from the soil, and what we found was that 150 years later, that forest functioned in a biogeochemical sense in terms of the emissions of greenhouse gases from the soil, just the way the undisturbed Amazonian forest did. It really recovered its ecological function as well as its water supply. Okay, well, now, we shouldn't be surprised about this because, in fact, this is common knowledge everywhere. If you look back at some of the historical records from Brazil from the 1500s, when they first cut down the coastal forests, even before the coffee boom, they cut down all the lowlands for sugarcane. And the historical descriptions say that this used to be a wonderful, cool land, and the rivers flowed, and it was, you know, just pleasant to be in, and now the forest is gone. It's miserable and hot as hell. Okay? I mean, everyone noticed the big increase in temperature that followed once the forest disappeared. Some years ago, someone came to me and they said, oh, they didn't realize global warming was so rapid because there's been a 20-degree temperature increase, I guess that's Fahrenheit, in Honduras in the last 20 years. And I said, that's not global warming. It's because 20 years ago, Honduras was covered with jungle, and now it's all gone. This is simply lack of evapotranspiration cooling the land, and that's not global warming. That's human-caused heating. Okay, so if you want to cool down, you've got to bring the forest back. If you want your water supplies back, you have to plant the forest back. And, you know, it's not new. Plato and Aristotle knew this, because in ancient Greece, every spring was a holy site to the ancient Greeks. It was an oracle, a goddess associated with every spring, and every goddess had their oracle who would predict the future, and people would go to those springs, you know, to consult the gods. And when they cut the forest down in ancient Greece, and this is long before Plato's and Aristotle's time, those springs all dried up. I mean, the oracles remained on these dry springs because these were traditional holy spots, but the water vanished. And if we want it back, we've just got to plant back our forests. So we've heard many examples of that. Sorry, I'm trying to go forward now. Why am I going backward? Okay. All right. Well, here's another example also from Brazil. I showed this last year. This is one of the world's most famous photographers, Sebastião Salgado. And he inherited this land that was so barren that the guy who herded their cattle said there wasn't a single stick that he could get shade in the daytime. He's out there, you know, in the burning heat, chasing the cattle. There's no water. The streams all dried up, and they went and they planted it in trees, and the springs came back. Last December, I was in Lima for the UN Framework Convention on Climate Change. It was a big presentation by the Inter-American Development Bank. Again, the same story. There was a huge watershed in Costa Rica that was all jungle. Beautiful springs and streams. And so the cattle ranchers moved in, and the first cattle rancher went and they cut down a whole bunch of trees and moved cattle in, and they'd run them down to the river to drink. And then more cattle ranchers moved in, and in a short time, the whole watershed was deforested, and the springs dried up, and the rivers disappeared in the dry season. And the result of that was they had to abandon the land because they had no water for their cattle. And they've replanted most of that watershed now. Most of it now is in forest, and once they planted the trees, the water came back. They just had to manage it that they didn't overdo it, you know, that they live in balance with the water supply. But it's something that people can do everywhere. You know, it's another case from India, and I showed that last year, of one man who planted a huge forest all by himself and brought back the wildlife. I mean, this is something anyone can do in any habitat. Examples in Jordan in the desert, just plain water harvesting. It's not increasing the rain, it's increasing infiltration. Planting the plants build up the carbon holds the water. So this is, you know, the carbon, really putting the carbon in the ground is sort of the first step for retaining the water. But then of course, we've got to deal with runoff. I'll come back to that a second later. But the more carbon there is in the soil, the more water will hold. And that has huge implications. So I don't want to get into this in detail, but the other thing is we've got to stop erosion cold, because erosion's washing away the soil, and it's washing away the surface layer of the carbon in particular. So we've got to basically keep the nutrients on the land and out of the sea, and the ideal method is what the Balinese do. I showed this again last year. The point is that water tries to minimize its energy. It tries to rush down the steepest slope. Okay, there's a physical principle, a minimization of energy. It goes down the steepest slope, tries to go as fast as it can. The faster it goes, the more water and soil it carries off. Okay, so the physics is just causes, you know, the gullies to form. What the Balinese do is they try to tap the water as high up in the watershed as they can, and they try to make it run horizontally, back and forth, instead of rushing down the steepest slope. So what you want to do is, the physics is obvious. You want to retain the water in the land as long as you can by you know, pooling it, ponding it, and make it move sideways back and forth across the landscape, so you hold the soil and water as long as you possibly can. And when you do that, you create these incredibly productive systems. But it's a lot of work. They need to be maintained. I mean, Peru in ancient times, there are thousands of miles of terraces in the Andes. Almost all are abandoned. They're collapsing. Okay? Once one goes, it carries down everything below it. So, it's a lot of work to maintain it. But when you do it, you've got a system that really is incredibly productive, and it's what we need to do. So I showed this also last year, where you get intense rain. This is the intensity of rain with time. And then with a forested watershed, that water is held for a long time, and it trickles out slowly. So you retain the water on the landscape, and even in the dry season months later, there's still water trickling out because you retained it in the soil. But when we cut the forest down, we get it all rushing off very quickly, and then we don't have any water, causing erosion, destroying the fertility of the land, and all of that. So vetiver grass, I mentioned, is the world's best erosion control plant, and you can actually stabilize severely eroding slopes with plants that have incredibly deep roots, because that's how the groundwater gets into the ground, is down the roots. Okay, so the worst thing to do is to let the land be bare. I mean, not only does that cause the carbon to oxidize, but it also prevents the rain from getting down into the ground where we want to retain it. Again, I mean, this is all sort of so obvious that it should be part of every elementary school education. This should be something that everybody knows, Okay. All right. Now, the thing is that the majority of the heat, solar radiation that lands on the Earth, on the land surface, and in the ocean, goes into evaporating water. Okay? That's where the heat disappears. And water, as Michael pointed out earlier, absorbs a lot of heat when it evaporates, and that heat is sucked out of the ground. When the water goes up into the atmosphere and then condenses, that heat is released. So you're transferring heat from the surface up into the upper atmosphere. And what that heat does is that drives the atmospheric circulation. It drives the winds, that heat that's released. And the point is, by getting the heat up high, there's a chance of it being radiated out into space, because if that heat goes up into the upper cloud layers, particularly in the tropics, because in the tropics the circulation gets very high. Now with global warming, what we're seeing is that the clouds are getting higher and they're getting thicker, and there's more of them. I mean, the world is getting rainier overall. Okay, some places are getting drier because they're far from the sources of moisture. But as I'll show you a little later, the ocean is really a key factor. Anyway, but the majority of the rain that lands on land goes back to the atmosphere in natural cycles, as long as we're maintaining that natural evapotranspiration. Where we cut the trees down, let it rush out into the sea, it's not able to absorb heat, and we run out of water simultaneously. Now, so understanding how the water gets in the air is really key. And the fact is that almost all of it is not physical evaporation. It's evapotranspiration. It's transpiration. It goes through the plants. Okay? I'll show you that in 1 second here. Okay, this is the global water cycle. And the fact is we live in an ocean planet. And the ocean is free to evaporate. So there's tremendous amounts of evaporation over the ocean. That's driven by the winds and waves, and we can't control that. We have no real way to manage that. I don't know, is Russell here? No, Russell was here, sorry, earlier. Yes, okay. So, I mean, the only way people have been able to try to figure out how to control that is Russell has this idea of bubbling the surface of the ocean to make it more reflective and reflect sunlight out to space. That's a tricky sell because you need a lot of bubblers. But otherwise, we don't really have the technology to manipulate evaporation over the ocean. We can't really control the winds and waves very well. Okay? But the fact is, global warming is increasing wind speed worldwide, okay, because it's changing the pressure distribution in the atmosphere, and that drives the wind speed, and particularly over the ocean. So over the oceans, we're getting more rain, more evaporation, and more atmospheric humidity. So that's a positive feedback on global warming. Okay? Now, the vast majority of that rain, sorry, is this the pointer? Well, I'm not sure which one's the pointer. Whoops, nope. Uh-oh. Maybe that? Nope. Okay, well, I don't figure out the point. There, the vast majority of what evaporates over the ocean falls over the ocean. So global rainfall over the ocean is increasing. Now, over the land, it's very hard for water to evaporate physically. The water is in the ground, and it's got to be sucked up by the roots. And in fact, transpiration, well, it's okay. That's Transpiration is really the bulk of what's happening with regard to the water flow. So, anyway, the point is, there's a large part of the water vapor that comes on land comes from the ocean. So, most of it falls in the sea, but some of it gets transported on land, and so that plays an important part. Then a lot of it is recycled on land, and that's a transpiration cycle. That's what we need to accelerate. I mean, we can't really control the water vapor transport. That affects areas that are near the shoreline, where the rain falls out most readily. But if we want rain way inland, it's got to be recycled through the vegetation. The rainfall in the Amazon, for instance, the so-called Biotic water pump, is recycled many times. By the time it gets to western Amazonia, where Foster is, it's been through the trees several cycles by the time it gets there. Okay, if you cut the forest down, western Amazonia would turn to semi-desert. So keeping transpiration going is really key. And it's only now we're understanding how effective it is. Now, these show plots of the stable isotopes, oxygen 18 versus oxygen 16, hydrogen in the deuterium form versus the single form. Now, the point is that the straight line that you see here is a global rainfall line. Global rainfall falls on this black line here, and there's a gradient in the isotopic composition of water going from the tropics to cold areas. And we can use that to trace the water and figure out where it's going. And this shows the O18 ratio to hydrogen ratio of the heavy to light isotopes for groundwater, and that falls pretty much along the rainwater line. Stream water pretty much falls along the rainwater line. But this is water inside of plants. This is in the sap of trees. And this is in the soil. And that's isotopically different. It's isotopically lighter. Because what happens is the lighter isotopes, carbon-12 and hydrogen-1, move faster than the heavier isotopes at the same temperature. And the plants take them up preferentially. And so they create a microhabitat in the soil that actually is chemically different than the bulk water and the groundwater. And so this water, what we're seeing in evapotranspiration, is isotopically lighter than what falls in rainfall because it's passed through the plants and through the soil. And this way we can actually trace where the water is coming from with the isotopes. It's really, really valuable. But, I mean, the point is that soil water is not the same as groundwater. It's been biologically selected and modified for the light isotopes. And this shows here, oops, still really, okay, this is transpiration relative to evapotranspiration. This doesn't really come out very clear, but here they're looking at whole watersheds and the isotopes. The key point is, and actually this isn't right, it's the top slide I want, but the point is worldwide, 80 to 90% of the water going through the atmosphere is going through plants. 80 to 90% is not coming from physical evaporation. So if we want to put more water and keep that cycle of heat flowing of water from the surface to the atmosphere, we really have to reforest our watersheds. Soil moisture trends and evapotranspiration trends. Some areas are getting wetter, but a lot of areas in red are getting a lot drier. Okay, that's all right. I won't go into this. Water use. CO2, every time a plant tries to photosynthesize, it opens its stomata to pull in CO2. CO2 is only 0.004% by concentration in the atmosphere. There's not much. So the concentration gradient's small. Every time it opens a stomata, hundreds to thousands of water molecules escape the other way. Okay? Depends on the humidity. I can't find a good number for that, but it's in the range of 100 to 1,000 molecules of water lost for every molecule of CO2 that's taken up. So the plants can't help that. Now, as CO2 increases, the plants shut their stomata down because their productivity is limited by nitrogen and phosphorus or other trace metals. Okay, so when they've taken all the carbon they can take up, they close their stomata and they stop losing water. So they become more efficient in water use as CO2 increases. But oddly enough, in Europe, there's been a long-term increase here in evapotranspiration. And that's because even though the plants are becoming more efficient at using water, which is the top line, they're actually, the growing season's getting so much longer that they're losing water faster than they're holding on to it. So there are a lot of unusual trends. There's another thing that since 1998, global transpiration has been going down in many parts of the world. Northern Europe is an exception. Okay, well, we've talked about restoring wetlands. I don't want to get into that now. Beavers. Okay, but I want to get into water and temperature here once again. This is a photograph I took in New Guinea a couple months ago, and I'm used to this being in the tropics. You see the forest smoking in the morning. At nighttime, the atmosphere is almost 100% humidity. So when the first light hits the trees and the atmosphere is cool and saturated with water moisture, as soon as the trees start releasing water vapor through the leaves, it condenses around them. And most people look at this stuff, they think it's fires. They wonder, who's burning the forest down? But it's not. This is something you see in the tropics every morning. It's the water being pumped out by the leaves into the atmosphere. I mean, it's a tremendously intense cycle, and when we lose it, we're losing the whole cooling effect. Well, let me show you something about the cooling effect here. These are measurements that I made with William de Mello in the Amazon in 30 years ago. And what I'm showing here, these are the air and soil temperatures in the forest. And that basically there's about a 2 degree or so oscillation in temperature here in the forest. It was always cool and pleasant in the jungle. This is undisturbed Amazonian forest. 100 meters away was an area that had been clear-cut. The cattle ranchers had come in, they'd cut everything down. The whole forest is lying on its side. The rainy season came before they could burn it. So they abandoned the land. They didn't have time to plant grass and bring the cattle in. But this is an area 100 meters away from that, and you can see that the daily temperature cycle here is like about 12 degrees C or so. It's just unbearably hot, and that's simply because the evapotranspiration has been removed. I mean, the cycle of the heat being pumped out of the ground into the atmosphere cools the surface down. And so it's something that we can restore. We don't really know what the magnitude of the restoration, but the effect is huge. I mean, it's like a 10 degrees C difference in the daily amplitude of temperature. Okay. So anyway, the point I want to make is that we've got to restore the carbon to restore the water cycles. And when we do that, we can have a huge effect on local temperature. Now, because most of the evaporation is taking place over the ocean, the vast majority, and because we can't really influence that, we can't really affect global temperatures that much. We can affect local temperatures on land by accelerating the water cycle. And to some degree, if we can get those water molecules to re-radiate infrared radiation from the tops of the tropical clouds, that'll tend to cool the Earth down to some degree. I wouldn't dare predict how much. But I mean, certainly, I don't think it's easy to manipulate water cycles to lower global temperatures, but definitely on a local and regional scale that is possible and should be done. Okay, thank you.